So today's topic is all about using neural networks for specifically for forecasting. And I'll go through some perhaps less known tips and tricks that you might find useful. So I will assume that you already are familiar with actually training your own models, doing that kind of stuff, and also familiar with neural networks already. So I won't cover that too much. Okay, let me just introduce AI for Impact a bit. So our mission is really all about trying to make AI accessible to non-programmers. And since 2017, we have trained about 1,000 over people in AI. Okay, my name is Arnold. I have a background in physics, and of course, I've been a weather forecaster for about 20 plus years. I've been dabbling in AI since the 1990s, and I still consider myself very much a student. Okay, so before we start, I want to just cover 5 basic concepts when it comes to forecasting. Well, the first one is about lead time. So lead time is how much into the future you want to do the forecast. It could be like 30 days ahead, 30 minutes ahead, sometimes even perhaps 10 minutes ahead, right? It's useful. So we use a T plus notation. So T plus, let's say 5 means T plus 5 days, T plus 30 minutes means 30 minutes equal like T plus, could be like 30 minutes ahead, right? So we use the T plus notation, and T plus 0 means the present. So if you look at this graph of temperatures in Singapore over the last few years, let's say this red dot represents the present, okay? So this yellow dot is, let's say, 180 days from the present. That'll be T plus 180, okay? Very easy. Now, measuring accuracy of your forecast, I'm sure all of you know about RMSE and, of course, the MAE as well. So I won't cover that too much. But the important thing is that to understand that, and I hope you'll see this very clearly in this presentation, is that single numbers always will miss out some valuable information about what you're trying to do. And this is especially true for time series forecasting because it involves an element of time. Okay, and we'll see also that sometimes local loss functions are not very, like RMSE, etc., are not very good for time series predictions. Okay, the third concept I want to introduce is this thing called persistence. So when you're doing a forecast, you can say, you can ask me, Arnold, what is the stock or market price for, let's say, Apple stock 1 week ahead of time from now? So T plus 7 days, right? And if I say that the future value, the predicted value, is the same as what you have right now, that's called a persistence forecast. So if, let's say, for example, you ask me, so what's a T plus 7 forecast, Arnold? I say, well, what's the value today, right? It's $30 or let's say $100, right? So that would be my forecast. So that's called a persistence forecast. So in other words, T plus some X is the same as T0. It's a definition of a persistence forecast. And what we do is, it's a very simple forecast. It's a useful benchmark, and we start with that. Now, persistence is easy to beat, obviously, for long lead times. For example, let's say you ask for a forecast of stock price, let's say 1 year ahead of time. Persistence is a bad forecast for that. But persistence is actually very hard to beat for very short lead times, and especially if the thing you're trying to forecast doesn't change very much, okay? So any credible forecast must beat persistence. Now, each field that you go to with to do any kind of forecast, whether it's like a demand forecasting or let's say failure prediction or let's say earthquake prediction, etc., they will all have some kind of benchmarks relative to that industry. And persistence is a general benchmark which pretty much you must use. Okay. Now, the fourth concept, is the concept of lag. Okay. So if you look at this graph here, you can see two graphs. The blue line represents the actuals. So time goes from left to right. Okay. So the blue is the actuals, and the orange line are your model predictions. And you see that, they look pretty much the same. Okay. Now it's obvious that what's happening here is that the prediction are just a copy of the actuals and shifted forward in time. In other words, it is actually a persistence forecast. And so the question is a prediction like this useful? And the answer is perhaps not, or it might depend really on your application, right? So how do we measure lag easily? Well, a simple method is to use something called a lag correlation. So I'm sure most of you are familiar with correlations. So lag correlation is where we keep, so the Y cap here represents the forecast and the Y represents the actuals. So what we do is we take the actuals and we lag them maybe backward in time, so that's a delta minus something, or forward in time, a delta plus something, and we calculate the correlation coefficient in this case. Okay. We can normally in the normal case we will actually normalize by the SDs of both the forecast and the model and the actual values. But here, so this is the kind of graphs you would get. Okay, so when you do something like this, you probably get a single major peak, or sometimes multiple peaks, and where you get the peak occurring, that delta, that shift measures the lag. So if I go back, for example, here with this thing here, the distance between the peaks, between these two, what is it called, between the actual and the predictions, would be your lag. So, and that would manifest itself here as your 5. Okay. All right. So lag is 5 units with 5 days, 5 minutes, 5 seconds. Who knows? Okay. And here you got two models here, model A and model B, and obviously the lag for model B is a lot better than model A. And so one of the goals that we have in forecasting is not just to look at the RMSE or the just errors, but also to look at lag and see whether they can be improved or not. Okay. All right. So pro tips: the first thing that you got to do when you do forecasting with neural nets for time series forecasting is to try and create a forecast with a low RMSE or low error, basically, right? And this should beat persistence. And the next step, if you can, is to tackle the idea of lag. And it's always easier to actually reduce RMSE than it is to reduce lag. Okay, and sharp correlation peaks are the best, and they indicate a high confidence in your results. Okay, the last concept I want to introduce is the concept of windowing. So the neural networks, I'm not talking about, for today's talk, we won't be doing recurrent networks, just simple feed-forward networks. So these feed-forward networks require a window of data to be received and as input. So what we do is we want to take a window selection of past data as input. It's a fixed length, and you basically just move this window forward in time to generate the inputs into the model for both training and for testing. So let me give you an example. It's not so clear. So let's say we've got this time series, right? It can be not just one time series, maybe multiple time series. It would just pick, let's say, a fixed window size. In this case, I picked a window of 18 months. And that's my T0. That's my present value. I'll obviously also include that as input into the models. And that's the back part of the window. It's T minus 540. And maybe I'm trying to forecast for T plus 180. That would be the value up there, right? So what I do is, I would take this data and I'll window it. In other words, I'll get the 18-month window, which is a big vector, and I have one output. So typically for forecasting, you really want to just forecast one thing, right? So under forecast, even for financial series, or let's say a demand, or let's say in weather forecasting, you want to build models that forecast just one thing. So in this case, I'm just forecasting the T plus 180. Now you could have multiple inputs and multiple different data sources, but you're just still forecasting just one thing. So the idea is that I will just move this window forward in time to actually generate all my training and testing data sets. Okay, so windowing basically generates the input vector and also the desired output as well. Okay, so it's just it does both things. So let me just discuss the problem first. All right, so it's very simple. We've got this data for Singapore temperatures. They are weekly temperatures. And we're trying to forecast 5 weeks ahead of the present, okay? So the way we obtain this data set is to actually just look at the different temperature gauges all around Singapore. We take a spatial average, and sometimes we even, we take like a median or something like that, right? Across multiple gauges. We then average this weekly. Now we have data for about 20 years. And if you look carefully, this data is strongly cyclic. And each cycle, each up and down represents 1 year. And the cycles are caused by the monsoons and the finest. So in Singapore, you might not know this, we actually have 2 seasons. There is the northeast monsoon, which goes from, I think, October up to about April, right? So October is an intermonsoonal period, and April is also intermonsoonal. So, but during those 6 months or so, we have got the northeast monsoon. That's when you get colder air coming and blowing in from China, actually. Okay, from the Tibetan Plateau, it goes across to China, and it comes in surges down to Singapore. And so you get this kind of cool weather, and that's all the dips that you see down there. But in summer, we also get the southwest monsoon, and this is much warmer air, and it also brings in the haze as well. That's when the temperatures go up sometime in June, July, August. Okay, so you can see this very strong pattern. But inside each year, there are actually a lot of fluctuations. And the fluctuations are caused by many different processes, right? There can be also things like longest, if you look at this 16, 15 plus year snapshot, you will see there is actually a longer scale variation. And also the yearly patterns are not consistent. They might shift from year to year, okay? So this is also what you would find when it comes to forecasting. Generally speaking, there are many scales of processes which contribute to the behavior of what you're trying to forecast for. Okay. Also, there are errors. Obviously, there's instrument changes over time. Singapore itself has changed, perhaps become more and more heat islands, etc. So it's also changed over time as well. Okay. All right. Now I will discuss how we solve this using a platform that we use in AI4IMPACT. We developed this platform. It's called AutoCAF. It's just a platform for learning AI for beginners. And we use a glue language. We don't use Python. We use something called Smojo. We've got the backend is just a modified version of Cafe 1. We use, of course, XGB, Rapids, etc., and so on. It's specifically for non-programmers, and it's be easy to use. Just a comparison. I know there are a lot of Power TensorFlow users out there, so just shout out to you guys. So TensorFlow, you have as a UI, you've got Jupyter Notebook or maybe TensorBoard. And then, so let me just give you Smojo, just an overview in a few minutes, or say 1 minute really. So this is the hello world in Smojo. So you've got, in Smojo, everything is from left to right. So it's unlike Python or Java where the functions are on the left. Okay, this is left to right. So hello world is a string literal. And the dot represents a function, or what we call a word, that prints the literal to the screen. Okay, very simple, left to right. Okay, so in Smojo, everything is either a literal or a word. There is nothing else. There's no punctuation, and we consistently follow a left to right type syntax or postfix syntax. Okay, all right. So this is a more difficult example. So let's say you would ask to find the first 100 squares divisible by 365. Now, of course, most of you can probably know how to program this, but here's how we do it, Smojo. First, you take 1, 2, and the dot, dot, dot creates an infinite sequence, 1, 2 to infinity. All right, so that's an infinite sequence, so it's lazy. Then you square it. You square the infinite sequence, so you have 1, 4, 9, etc. And then you filter off those which are divisible by 365. And you just take the first 100 of that list, and you truncate the list, and then you print it out. The dot list prints out the list. Okay, so this is how we do stuff in Smojo. It's quite unlike Python, or let's say, I'm just choosing Python, it's just an example, but most other languages will take this approach as well, like Java or whatever else you want to use. You would have an explicit loop. So the problem with explicit loops is that for beginners, at least, is that there's a lot of bookkeeping involved. You have to have the variables n and m and x, right? So that's harder for beginners to understand. And that's why we say that it's actually a beginner's language. Smojo is a beginner's language, right? Okay, now enough of that. We'll move on to the neural networks part. Throughout this talk, I won't use fancy neurons. I'll just use the most basic one, which is called the Perceptron. I think most of you know this. It's just a dot product with an input vector followed by some weights, which we call a linear combiner, okay, an LC. and followed by some theta, which is a saturator, right? It could be like a ReLU or 10H or leaky ReLU or what have a sigmoid, okay? And the important part of the saturator is that it's nonlinear, okay? All right. And we will only consider feed-forward networks. So in this case, the different perceptrons are all arrayed according to layers, layer 1, 2, 3, 4, and so on. And you always end up with a final layer for output because the outputs from the unless you're using something like ReLU or something else, the outputs from your neurons are saturated at some stage, either on the negative side or both sides. Like ReLU is saturated on the negative side, and 10H is on both sides. So you need to have some kind of linear combiner to actually increase it. So now some pro tips for you guys. This should not be unfamiliar to most of you if you've used it. You should use at least 2 layers, not counting the final LC layer. And you want to shrink the layers, don't expand them or stay the same. And the shrinking factor should be anywhere from 2/3 to 1/2, depending on the problem that you have. And leave enough neurons at the top. I like to leave about 4 or 8 neurons at the top layer. Okay, otherwise things get a bit dicey. And if you're training in one pass, then limit the depth to about 6 or 8, I would say would be safe. Okay. All right. Discussion time again, Ku. Any questions at this stage?
Okay, from experience, are there scenarios where we should look at MAE instead of RMSE?
Yes, great question. So if the problem with RMSE is that it penalizes you when you are far away when the errors get larger and larger, right? So I think that when you're dealing with financial data sets, especially, you want to look at MAEs instead of RMSE. Also because in financial data sets, you often have outliers. The big problem in financial data sets is outliers. Shocks because of, price crashes or political news and so on. And so because these are so common, you want to have a loss function that is less sensitive to these outliers. Otherwise, they would dominate your learning. So yes, but for this problem, when it comes to weather forecasting, for sure there isn't a shock. We're not dealing with lots of shocks, so I will just stick with the current RMSE.
Okay, good question. We have one more question. So let me show it to the rest. Okay, let me read out to you. It's easier to get high accuracy for less than T+7 weather forecasts. How about T+30 forecasts? Example, predicting weather for cross-Pacific voyage planning. What's the best way to model such forecasting problems?
Okay, so that's a very good question. Let me just answer the general. So I won't talk. Let me answer the general question first. You're right. It's actually weather forecasts are best for T+7 and below, and that's really not because of AI. It's really because of numerical weather prediction, right? And it also depends on the parameter you're trying to forecast for. So, for example, let's say you're trying to forecast for wind speed or wave height, then of course your time horizon for accuracy is going to be smaller. But if you're trying to forecast for something which is more slowly varying, like temperature, and let's say in the US or let's say Europe or China, then these mid-latitudes, the temperature changes are much slower. So therefore, you can actually extend the horizon well beyond 7 days ahead. You might even be able to extend to about 30 days ahead or 90 days ahead in some instances using statistical techniques or using AI, right? Now, to answer your question about voyage planning, 30 days ahead, the best answer I can give you is to use some combination of historical data plus selection of that historical data based on some AI techniques. But the problem is that the quality of data sets we have is very small because we only had weather satellites for weather prediction since about the 1970s. That gives you only about almost just 50 years of data to work with. That's not very much. Okay.
Okay. Ken, I think that's all the question we have for now. Okay. So we can continue then.
Okay, cool. So I will first describe what I call the naive network. And The naive network is basically you take your past data. That means how beginners would normally do a forecast, right? So you take the past data, you shove it into your feed-forward network, and then you get the forecast. Okay. So this is a very simple setup, and it in some situations it does produce good answers, but in a lot of situations it doesn't give you a good answer. Okay. So let me explain why. Well, the first problem is that when you do it this way, your network has to learn which is t plus 0. Okay, so that's bad because the t plus 0, it means the latest value is very important. And you want to give as much information to your network as possible. So because you waste time learning t plus 0, a lot of your experiments will fail and you end up with a persistence type forecast if you're lucky. Okay. The second thing is that when you do this, your time series has to be detrended. In other words, let's say you've got, especially for like stock or functional data sets, right, where you've got these upward trends or downward trends, etc., right? So you need to detrend these things. Otherwise, you don't have enough examples to learn from. Okay, you have to detrend them. And it handles spikes and rare events very poorly, obviously because they are rare. And so it's hard for the network to learn these rare values and to cluster them accordingly. Okay. Now, I also want to talk about something called the prediction pipeline. So this is just for those of you who perhaps don't do a lot of forecasting. This is how we normally do stuff. You first have a prep stage, okay? And the idea is that you put all your normalization scripts, missing values, noise removals, or maybe you're trying to have some synthetic inputs like wavelets, etc., and so on. You put it in the prep stage. After that, it goes into a windowing stage where you have a windowing being done, or perhaps even feature engineering. Okay, so in this talk, I won't talk so much about feature engineering because that's a whole new thing. What I would just focus on is just taking a simple window and trying to work with that. Okay, but obviously you shouldn't do that, right? Okay, and finally, once we have that window data, it means it's chopped up. Okay, so in the prep stage, the data is still in the time series sequence. In the windowing stage, it is chopped up, and you've added some features, etc. And the training stage, you train your model. Okay, it's all about risk minimization at that stage. And then, of course, you start to do some kind of prediction, all right? So most of the time, you'd spend actually in the least amount of time is in the prep stage because you want to just fix it once and for all. And today, we'll be talking about the training stage almost exclusively. Right, and we'll do a bit about the feature engineering as well, where usually you have a lot of changes. But today, because I'm introducing new concepts, we'll be doing more on the train stage and a bit on the feature engineering part. Okay. So in AutoCAD, we have it's a very similar mapping. You've got a prep script, and that goes into a windowing script called pre.m. I'm telling you this because I'll go through the system later on so you can see it for yourself. And so you don't get, it gives you a fixed point to think about, okay? And then you've got the training, and the train stage is defined by two things, by a network and by a config. So the network is basically your network configuration, and your config is basically possibilities or settings that you can set for the network itself. And then, of course, you run the prediction, okay? All right, all of this stuff is orchestrated by a single file called main.m. Okay, so we cleanly separate this stuff out because otherwise you get a mess. All right, so let me just demo now on AutoCAD the naive network so you can just take it through. Oops. Okay, I've already run the first thing I'll do is I've got actually a few data sets here. A crude, which is for crude oil prices, which I won't do today. I'll focus just on the temperature data set, okay? So let me just run this thing for the temperature data set. So the first thing you want to do, obviously, is to check out the stats that you have from this model itself, okay? And I'll run the prep. And I find that the mean temperatures are around 27 on the training data set with an SD about 0.8 and a mean of about 28 ish and 0.7 for the test data set. What I'll do then is to just fix these numbers on the normalization, right? So this is Smojo on your left-hand screen here. So what this does is just to take that data minus, remember it's from left to right, so it's 28 minus 0.8 divide. So I'm just giving a mean of nearly 0 and an SD of about 1, okay? And map just applies that to the entire column, okay? Now, so once I'm happy with that, okay, I then want to calculate what is the 5 week persistence. So this is the T plus. So I've done a simple persistence calculation out here. Let me just run this again because I'm lazy. And so I get for the test data set, it's about 0.675. Okay, that's my persistence loss after it's being normalized, not before, but after. So that's why I put the persistence down here. Okay, so recall that persistence simply means that the forecast for T plus 5 is just the current value, the present value. Okay, and that error is 0.675. Okay, so what I want to do then is just to call up my notebook and save that value out here. Now I've already obviously keyed this stuff in so I don't mess things up, but you can see the value here is 0.675. Okay, so now let's just close this and we move on to training the network up. The naive network that is. I'm opening up main.m, config.m, pre.m, and network.m. So let's go through this one by one, right? So the pre.m is just where the windowing is done and the features are done. So in this case, I've selected there's only one column of data. If you look at the data set, let's say this one here. There's just one column of normalized data. These are normalized temperatures after the subtraction by the mean and the SD, right? And so I'm just selecting A5 here. Let me just blow this up for you. I'm just selecting A5 as my labels, and I want to get a window from A0 to A minus 20, in other words, 20 weeks back in the past as my feature. Okay, is this a raw window? Now, normally you wouldn't use raw windows, you use features, but I'm just using a raw window just for simplicity. Now, I've already set this network up for dropouts and everything else, and I've tuned it as best I can. Okay, so I've used a dropout of 0.1 on my main network, on my feed-forward network for all the layers. I've set the base layer, the first layer, to be a size 64. And the input size is 21 because I have 21 inputs from A0 to A minus 20, right? So that's 21 values. Okay. And I'm going to use the Adam solver. Okay. Use SGD only when there's a need for speed. Otherwise, Adam is good enough. I'm going to repeat the experiment 30 times. So typically for this kinds of forecasting and so etc., you don't want to just rely on one or two. 30 is a good number to get. So you get a feel of what kind of variability you have. The dropouts introduce, even with Adam and with maybe a Xavier initialization or even a constant initialization for your weights, the dropouts obviously will introduce a lot of variability in the results. Okay. Okay, so let's just run this. So the first step is for me to prepare the data set, to do the windowing itself, and to save it onto the server. So that's done. And then I'm going to train my models up or submit them for training. Okay, so I've got my 30 configurations all done, and I'll check for the status as it's being processed, right? So this is asynchronous. So you can go off, have a cup of coffee, and come back again. And it's fast because the data set is quite small. We only have about 1,000 plus values in total. Okay. Let's check the losses, and this is where it becomes interesting. Okay, so the losses don't look too good. So you can see that you're getting the models being trained, right? So the blue is the training loss. The red line is your test loss, and it's been stopped here because of early stopping. I've set the max ITERs to about 10,000, so that should be a problem. But I've got early stopping keep putting in, right? And these are my loss statistics for all the runs. These are all just repeats, so there's no need to go through them. But my lowest loss is 0.61, right? And that's not much better than persistence. So in fact, here it's 0.61, but I had a better value before. Okay. All right. So let's try and do the evaluation. That means we run a prediction this time to see, you know, how is the model actually performing, etc. Right? This is asynchronous as well, so you need to test it out and see whether it's done. Okay, it's all done. Okay. So you see, because of early stopping, the model hasn't had a chance to train properly. So you can see it's actually the red lines are the predictions and the blue lines are the actuals. And the red lines haven't filled up, right? And you can see the blue lines are actually quite spiky. Okay, this is the test data set, and you can see it looks really bad. To be honest, a lot worse than persistence. Okay, and this actually beats persistence, yeah. Okay, that's a scatter plot for training, scatter plot for testing. It doesn't look too good. And this is the lag plot. Okay, so the lag plot is interesting. If you recall, you should see the peaks, right? So the blue one has got a single peak around 0. The training peak is 0. Okay, and that means it's actually learning the learning correctly. And here you've got really one minor peak here at around persistence. Well, this is about maybe lag 5, and the major peak is around 13. Okay. So what this tells you is that the lag for this is between, well, you've got two different lags, one at about 13 and only one around 5 or 6. Okay, not a good forecast at all. Okay. So that's that. So let me just close this down. Okay, we have a discussion now for about a couple of minutes. Cool, Pira?
Yeah, sure. I think we got two questions. So the first one is, additional features used other than time series data? So like, for instance, maybe a month, week, day, hour numbers, location, etc. Any potential leading indicators?
You have to be very, 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 very careful about how you introduce things which are monotonic. Like time, for example, is monotonic. Or things like which are cyclic, like the day number, for example, or the day of the year, right? And why that is so, or day of the week, even worse. Okay, because you have the day of the week 0, 1, I say 1, 2, 3, 4, 5, 6, 7, and the next day is back to 1. So it's a discontinuity there between the 7 and the 1, although they are adjacent in time. Mm-hmm. Okay, so for things like time, obviously you're not going to use the date stamp. Okay, I hope you guys are not going to do that, right? So that's off the cards. But even when you have things like the day of the week or the day of the year, you have to be careful. I think day of the year might not be so bad, but I think day of the week is definitely, you don't want to do that, right? So one way around that is to use instead the angle, all right? So you think of it as a circle, okay? Then think of your 0, 1, 2, 3, 4, and so on, the day as an angle around the circle. And instead of having just one number as an input, which is cyclic, what you do is you instead put in a UV component when you're on the circle. So you have two inputs, okay? So that's how you handle things like a time. So the inputs, when it comes to things like time and so on, you have to be careful. Other inputs, comes like position and so on, I'll be very cautious about doing stuff like that. Okay, you really have to understand what you're trying to do before you just shove it in, or your network will be usually stuck in memorization. Okay, it just memorizes and it trains very well, but the other stuff is rubbish. Now, one way to eliminate stuff like that is to use perhaps pruning, or later on we'll see weight input scaling.
Okay. We have one more question. So the question is synthetic input in prep stage different from testing training in training stage?
So the synthetic input is where you create some new input based on your domain knowledge, right? So oftentimes, let's say you got missing values, okay, and you want to have data imputation, right? So you might instead, let's say I've got station A, it's got some gaps in data, right? And I got station B, which has got some other gaps. So I can then fuse these spatially to create a synthetic station, so to speak, which I can use. Another way to use synthetic inputs might be, for example, to run like a windowed Fourier transform or some kind of wavelet transform on a window or some other thing, right? And then from there, actually take the coefficients of those things as inputs. That's what I mean by synthetic inputs. So for this talk, I only have one column, but typically for the inputs, you have many columns, okay, as inputs. So you have column A, B, C, D, or column 1, 2, 3, 4, etc. But for simplicity, I'm going to use one column for this training example. So if I want, for example, if I'm trying to like forecast weather in Singapore, I wouldn't just do a single kind of what's called a weather data. I also include things like maybe the cloud cover. I would include things like the temperatures elsewhere. I would include things like wind speed. I'll include even the stuff like temperature in China, for example, or Indonesia, because those two things do affect weather in Singapore as well. So multiple columns typically.
Let me show this. Okay, can you elaborate a little on how you normalize your time series? Are all values relative to T naught, or would you use other baselines such as moving averages?
Okay, I think how you normalize it really is up to you as long as it makes sense. So normalization is, okay, so you have to understand what is the purpose of normalization. So if you're dealing with, let's say, if you're using, for example, let's say, I don't know, like a random forest, like XGBoost or something like that, then don't normalize, okay? Because XGBoost and those kind of decision trees, they don't care. But normalization is very important for neural networks. In fact, it's super important for neural networks. And so there are two reasons why you normalize. The first one is because if you're using a saturating, of course, since the neural networks have saturators, all right, if the numbers are too big, they will saturate straight away and you get rubbish. It won't learn quickly enough. Because once it saturates, the gradient along the tangent H, or let's say the ReLU on the back side of it, is zero or near zero. And so because your gradient descent and backprop depend on the gradient of your activation function, because you're already hitting near zero, you won't get any learning at all. Okay, so you want to make the numbers small. The other second thing about normalization is that the inputs need to be about the same size. Okay, because if you have one which is a bigger size, because you can a dot product, right? If it's a big number, let's say 10 times, 20 times bigger than the rest, it will dominate the rest of those numbers and swap them out. Okay, so that's no good as well. So you want to actually make sure that they all normalize at the start. So what the normalization you do, all you need to make sure is that it's the same normalization that you use for your training, for your testing, and for your deployment. Because otherwise, you'd get you need a different model, you see, because your model, let's say you got a stationary time series, okay, for the training and for the testing. If I use one normalization for my training and a different one for my testing, obviously, my learning will be very good lah.